The recording will not just shut down arbitrarily here. Okay, so example 2. We were learning how to approximate areas of regions yesterday in this systematic process by partitioning it up into rectangles, which were the easiest geometric shape to use, all of an equal width delta x. And so depending on the number of rectangles we want to use, that's going to determine how accurate we're going to be. And that's going to be usually, when you're asked to do this, given to you. All right, so you're not going to have to make that up. Bless you. But to figure out what the width of each subinterval is going to be, all you have to do is take your total width that you're trying to find the area on, which is from A to B, and divide it by the number of subintervals you're using, which we called n. So we called the width of each rectangle delta x, and in general it's b minus a, your total width, divided by n, the number of subintervals. Okay? And once you have that, you can determine the height of the rectangle on each interval in any one of 3 different ways. You can use the left endpoint of the interval, the right endpoint of the interval, or the midpoint of the interval, and those all use rectangles. There's another way that I'm going to show you that we'll check out here in example 2. All right, ready for example 2? We're actually going to do some numbers here. Using 4 subintervals, see, they told us, of equal widths. All right, we're going to approximate the area under the parabola y equals x squared from 0 to 1. Okay, so we look over here, graph's already given. We've got y equals x squared. We're looking from 0 to 1. We're trying to find the area of the region bounded by the graph in the x-axis. They called it S. All right, so if you're just looking at that and you had to come up with a single approximation, and you weren't real picky, you might just say, I spy a triangle. And you might find the area of that triangle, and you know that you're going to be off by about that much. And that might be okay with you, right? Because it's a very easy calculation. But that's not what we're going to do. So what we're going to do is partition it into 4 equal subintervals. All right, so here's how you can visualize it. You draw a line straight down the middle, and then you draw another line here and another line there. So you're bisecting and bisecting, and that splits it up into 4 equal subintervals. So we do a little bit of prep work here before we get to the answers. The next thing you're going to probably want to do is figure out what those x values are. So the width of each interval, which I'll call delta x right here, delta x, delta x, delta x, and this one I'll squeeze in delta x. Delta x in general, remember, is b minus a over n. Well, for us, we're spanning from 0 to 1, so that's 1 minus 0, and we're using 4 subintervals. So the width of each subinterval is a fourth. So all you have to do now is label those x values. You take your starting value, which is 0, that's nice, and to get the next x value, add a fourth. So we get a fourth, and then add another fourth, and you get 2/4, which is a half, and then 3/4, and of course you get 4/4. So 0 is like our x sub 0, 1/4 is like our x sub 1, blah, blah, blah. All right, so now we have that. We're going to go ahead and come back up here. We're going to use, first of all, L sub 4. We're going to compute L sub 4 as an approximation of the area. Now the L stands for left endpoint. Left endpoint. So we're going to use the left endpoints of the region to define the height. The subscript to 4 just means we're using 4 subintervals. The R is going to mean right endpoint. The M is going to mean the midpoint. And T is going to be a surprise. All right? So here we go. Let's go ahead and draw it first. The left endpoint, because it's good to visualize. If you go on the first interval, the left endpoint is x equals 0, and you're going to use the function value's height at x equals 0. So notice that kind of looks like a crushed can. The height is 0 all the way across. The next interval from a fourth to a half, you draw a line straight across to the left, and you continue doing that straight across. Now, if you want to shade that kind of in a light blue, you'll see that we're finding the sum of the areas of what turns out to be only 3 rectangles, because the first one is crushed down to nothing. Now here's what's interesting. You can tell immediately just by looking at the region, since the graph is increasing and concave up, that our approximation is going to be an over or an under approximation. It's an under approximation, definitively, right? Sometimes it's not that obvious if the curve is increasing and decreasing, but in this case it's very obvious. It's going to be an under approximation. So this might be a good lower bound for the area. Huh? All right. We're going to go ahead and write it down below here, and then I'm going to copy and paste it and move it out of the way. So here we go. We're going to say that the area, that's an A, is going to be approximated by L sub 4, which equals. All right? Now, the area of each rectangle is just going to be height times width plus height times width plus height times width. So I'll do the width first. The width is delta x. What's our delta x? 1/4. And the height, I'm just going to call f of 0. Okay? That's the y value at the left endpoint. Plus, the next area, the one that's actually highlighted there, the width is going to be 1/4. And the height is going to be the function value at its left endpoint, which is f of 1/4. Plus, we keep going. The next width is 1/4 times f of the left endpoint of the next interval, which is 1/2. And then finally, the last rectangle has a width of 1/4. And the height has a function value of f of 3/4. All right, so notice a couple of things here. We have 4 computations for 4 rectangles. The first 4 x values out of 5, it takes 5 x values to define 4 regions. We're using the first 4 x values heights, which means we're not using the last one. In other words, the x values are left justified, right? Left justified? I mean correct? Sorry, not right. Left justified? We're using the first 4, not the last one. What else do you notice about something about each of those terms? Do they have any common factors? They have a 4th. So here's what we can do, and this is a pattern that is going to be useful when we do the other computation. If you have a uniform delta x, which we do, we computed it, you could factor it out front. And notice then what's left is just the sum of the first 4 y values. That really expedites the process, okay? Now, in general, what we're going to do is, this is true for really any function with these stopping values of x. All we have to do now is make it specific for our function, which is to evaluate the function values. What's our function? It's input squared, right? So let's do that. This becomes 1/4 times, let's see, f of 0, that's 0 squared. I'm just going to call it 0. Hey, I know that. 1/4 squared is a 16th. 1/2 squared is a 4th. 3/4 squared is 9/16. Now, if this were a free response question and there's no units to put on the end, is this a good place to walk away and get full credit? Yes. Okay. We're going to keep going, though, because we want to practice for multiple choice, and we want to know what the answer is. So we get a 4th, and let's see, that's going to be 1/16 plus 9/16. That's 10/16, which is the same as 5/8. Let's get them all in terms of 16ths. How about 10/16 plus 1/4 is 4/16? So that's 14/16. And 14/16 is the same as, oh, did I multiply by times a 4th? Sorry, times a 4th. Don't forget the 1/4 that front. 1/4 times 14/16, which simplifies to 7/32 after a little bit of work. 7/32. Now, if you want to know what that decimal is, I guess do long division or pull out a calculator. I'm content right now with 7/32. And I know that's going to be an upper or lower bound. Too big or too small? Too small, yeah. Now, of course, if you were pickier and you want to do better, just increase the number of subintervals, right? And you just have more things to compute. All right, let's go ahead and approximate it now using the right endpoint. I'm going to call that area squiggles r sub 4 equals. All right, so let's see what that's going to look like. If I go to the same graph, the right endpoint now is going to be 1/4, and that's going to be the height. So I get that, and I draw back to the left and down, draw to the left and down, and then over here to the left and down. So if you want to shade that, that's going to be definitively what, an over or an under? That's going to be an over approximation. The graph is increasing concave up. All right, that's going to be an over approximation. So I think we can kind of go straight to the computations over here. Are we going to have a uniform delta x all the way through again, width times height plus width times height? Yep, so I can factor it out. Now notice the first y value I use is not f of 0. Everything is right justified now. I'm skipping the first one and using the last 4 x values. So it'll be f of 1/4 plus f of 1/2 plus f of 3/4 plus f of 1. Is that a good place to stop on a free response right there? Is that numeric? No. So now I apply my function, which is to square the inputs, and I get a 16th plus a 4th plus 9/16 plus 1 squared is 1, which is the same as 16/16 if you want to do that. So we end up basically with 14/16 from above plus another 16/16. That's going to be 30/16. And that simplifies to 15 30 seconds. Yeah, 15 eighths, and then 8 times 4 is 30 seconds. So I got 7 30 seconds is too small, 15 30 seconds is too big. If you were required to report one number as an approximation of the area, you could report either one of those for sure, but what might be good practice if you know these two? Would the average of those be a good approximation? Yeah, I think an average would be good. Let's see what the average would give us real quick. The average of the two would be 7 30 seconds plus 15 30 seconds divided by 2, right? And that would give you, what, 22 30 seconds divided by 2, which is 11 30 seconds. So I don't know how close 11 30 seconds is to the average, or to the actual, sorry, but I do know that it's probably a good compromise, because notice one of them is too big and the other one's way too small by what appears to be roughly the same amount. And so could work. We'll find out in the end here. All right, the last one here, maybe before lunch, is the midpoint. Midpoint's going to be a little bit more tedious because you have to find new x values. So what we're doing is we're going to the midpoint of each of these intervals, and we're using the height of the function at that point. So if you want to draw it, just go to the midpoint of the x interval, draw a dot on the function, and just go straight across left to right. And as I mentioned yesterday briefly, this one, if you're doing just one calculation, is not a bad one to do, because it's kind of getting too much on one part and not enough on the other. And it's almost like averaging it on each interval. It's not necessarily an average. So if you want to see what that looks like, it's going to be this one here. Is it possible to tell if this midpoint one is going to be too big or too small or just right? Is that real obvious? No, that one's not real obvious. Do you think the midpoint method is going to be the same as the average of the left and right? Not quite. Why? Well, if you average the left and right, you're kind of assuming a constant rate of change from one endpoint to the other. It's almost like drawing a diagonal between there and getting the average. The midpoint is actually following the curve, which is not increasing at a constant rate. So the midpoint might be close to the average, but it's not necessarily going to be the same. All right, so all we have to do is figure out these y values. Half of a fourth is an eighth. So if you count by an eighth now, you're going to get an eighth, and then you get 3/8 over here, 4/8, this becomes 5/8, 6/8, and then you get 7/8. So now that we have the new y values, we can go straight to the computation. Watch this. The area is going to be approximated by the midpoint. The delta x is still 1/4. Still 4 subintervals, still 1/4 wide. But now it's f of an eighth plus f of 3/8 plus f of 5/8 plus f of 7/8. And now I can say 1/4 times. Applying the function, I get 1/64 plus 9/64 plus 25/64 plus 49/64. And that comes out to be, let's see, 50, 75, 84, a fourth of 84/4, which, that comes out to be 64/4. Thank you. 84/4 comes out to be 21/64. Oops, what are I at 26? 64. Now notice that is not the same as the average, but it's pretty close. 11 30 seconds is how many 64ths? 22/64, and this is 21/64. So it's not the same, but they're really, really close. And we're going to find out after lunch how close they are, and we're going to learn what T sub 4 stands for, and then we're going to figure out what the actual area is. So You're not going to want to miss it. Make sure you come back. All right? Take a short commercial break in between here.